Okay, we are going to continue on here. We're in chapter 2, and we started talking about sort of units. Uh, okay, so in this chapter, we talked about the importance of units. We talked about some different types of units, really two types of unit systems. There's the English system that we use, and really the metric system. As we talked about, essentially in science and in chemistry, we kind of go with the SI system, which is sort of that international system of units. That's sort of a standardized system of units, sort of based off the metric system. Again, just to have some consistency in terms of when we look at units and people use units in science, they're kind of using sort of the same type of unit scale. We also have the importance of when we do use a unit to know what it means. Is it a mass? Is it a volume? Is it a length? So understanding again what each of those units sort of mean. We also saw the prefixes that are very commonly used, especially in the metric system, to sort of change the meaning of certain numbers. Like for example, centi is 10 to the minus 2. Remember that the way we properly use this is that number, which isn't scientific notation, is how much there is of the base unit to one of the prefix units. So for example, 1 centimeter would be 10 to the minus 2 meters, and that is basically 1 times 10 to the minus 2 is basically what that is. That is the same, again, if you want to divide the 10 to the minus 2 to both sides, I'll get you 100 centimeters equals 1 meter. So both of those conversions are really the same conversion, just sort of either you want the sort of larger number or sort of the power 10 exponent. But again, when people sort of use this, it's very common to people will do it sort of backwards and do something like, again, 10 to the minus 2 centimeters in 1 meter. So again, you want to always kind of use that for the prefix. Doesn't matter what the base unit, in this case, the base unit is meters. If you had 1 centigram, that would be 10 to the minus 2 grams, where grams here would be the base unit for each of those. I think we sort of finished up there talking about how to take a measurement and a proper way to take a measurement. There is some type of uncertainty in measurements, as we talked about. When you do take a measurement, you always want to look at the scale that you're dealing with on the piece of equipment. And really, when you look at that scale, there's really two types of markings. There's large markings and there's small markings. And typically, the large markings will have numbers on them. The small markings are like the little sort of markings between those large ones. So again, like on a ruler, you know, large markings here would be 1 centimeter. There are, again, if we count from here to here, 10 markings, which means each one is 0.1 centimeters. And as we might have talked about last time, typically speaking, you really can go one more place, usually to the right of the smallest marking when you take that reading. There's going to be some certain numbers that no matter who looks at the particular scale, everybody should agree in terms of the measurement. And there will be really one uncertain number, thank you, where, again, that's really where the uncertainty, the estimation comes into play. Some people may look at it and see one number, others may see another number. Any questions on any of that there? So I think we were kind of doing some examples there in terms of measurements. So again, if we had something like this, and we got our 10. Okay, so let's take a look. So once again, when we do look at any piece of equipment, and it can change depending on the glassware, and even again, the same sort of glassware being the same volume, made by different manufacturers, may also have different scales. So you should always look at it. Equipment is like here we can see our large markings does represent here 10 milliliters. Remember that when we are counting between our large markings to figure out our small markings, we always start counting after the previously sort of marked large marking. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we do stop at the next large marking. So again, here we do have 10 markings between our 10 milliliters. So if we basically take 10 divided by 10, that means each of our small markings represents basically 1 milliliter in this case, with this guy being like 11, 12, 13, 14, 15, 16, 17, 18, and then 19, and then obviously 20. So if we take a look at it, again, everybody, no matter who takes a look, should agree it is at least 15 in this case, and we should record that. So as we talked about, you should always record all what are referred to as the certain numbers. Now, again, we're not exactly as we would be reading from the bottom of the meniscus as we talked about last time. We're not exactly at 15, not really exactly at 16. So this again is where the estimation comes in, the uncertainty in this measurement. And maybe I feel it's just a little bit over half. Maybe I record 6 milliliters. This would be my first uncertain number. Remember that when you record and take a measurement like that, which you're supposed to do all the certain numbers, plus that first uncertain number, that's basically significant figures. Figures in this particular case, with the uncertain number being that last one in this case, the 6 being where that uncertainty is. I think we also talked about that if you can identify what the smallest marking represents, you basically can divide it by 2, and that will give you, in this case, like 0.5 milliliters. That is kind of like your uncertainty in your measurement, plus or minus 0.5. It will also tell you basically if you do that. So if you feel really confident about, what the smallest markings represent, you could divide it by 2, and I'll basically tell you how far you should take your reading to, which again, in most cases, is one more place to the right of the smallest marking. We can add that to our measurement, plus or minus 0.5 milliliters, to give us our proper measurement here. Any questions on that there? Again, usually most people think of the sort of the uncertain digit as being plus or minus 1 of sort of where it's at. The uncertain digit, by the way, is not always the last one written, but it is the last significant figure, as we'll talk about in most cases. There. So if we take a look at another one here. Go right about there. All right, so same thing, take a proper reading based off of this scale here. Okay, so once again, let's take a look. We want to always sort of figure out our large markings, which again, in this case, is a 10 milliliter spread between 10 and 20. In this case, we start counting here. So that is 1, 2, 3, 4, and again, 5 markings in this case. That means that each of our smaller markings actually, we take 10 divided by 5 is 2. That means that really this marking here is 12, 14, 16, 18. That means again here where we drop right there between 16 and 18. Between 16 and 18 is which number? It is 17 milliliters in this case, yeah. And that would mean, for example, this would have how many significant figures? Would have 2 significant figures, with a certain number being the here, right, is really the uncertainty. So on this particular scale, although the big markings is still 10 milliliter difference, because we have less markings between them, Each one is 2. And the best that we really could do in this case is to the whole number here. And that is because we really do not know in this case where 16 would stop, where 17 would start in that sort of space. It's just too many numbers for that little space between it. When we're only dealing with like a, say, 1 milliliter difference, you could kind of go, okay, halfway there to the next milliliter, you could kind of visually see that. But here we got multiple numbers happening between that small marking, so you can't really figure out where one starts, where one ends. We also could divide, again, our smallest marking by 2, which tells us this should be plus or minus 1 milliliter, which means we should go to the whole number, which is like what we did there. And we can record the uncertainty with our measurement of something that looks like this, plus or minus 1. Any questions? Dead on in that case. So if we look at this and we take a look at our measurement here, once again, looking at our large numbers on our ruler, our large markings are 1 centimeter. Again, counting 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 gives us our small markings. 1 divided by 10, 0.1 centimeters is basically what the small markings represent. So if we take a look at this, we can see 1.1, 1.2, 1.3, 1.4, 1.5. So if we're right on there on the 1.5, we can record 1.5 centimeters, 1.50 centimeters. Is there a difference in terms of which one you do record? Well, let's talk about if there is or not. Let's start with this guy. How many significant figures would this guy have? Would have 2 significant figures. Here, the uncertain digit would be which one? Would be a 5, right? Over here, this guy would have how many significant figures? Would be 3 significant figures. Uncertain number here would be the 0 in this case. So if we were to take this one, which is 2 significant figures, what you're really saying is I think it's 1.5 centimeters, but maybe it's like 1.6, and maybe it's like 1.4, plus or minus sort of that last digit. And if we look at this, by the way, where it is sitting, that's a pretty big room for error, right? It's really nowhere near either of those numbers. It's not near 1.4. It's definitely not one near 1.6. So we would not want to record this number as that is a big amount of error, more error than we should have with this piece of equipment. We look at the 1.50, which has 3 significant figures, with the uncertain number being this guy. What we're really saying is it's 1.51, maybe it's 1.49, which is pretty much right about there, right? Which is where our measurement really is if we kind of look at our scale. So in this case, we do want to make sure we record it as 1.50. If you loft off a 0 in this particular case, you're making your measurement pretty crappy. You're making it a lot worse than it should be. You're putting a lot more error in it than should be there based on the equipment that you're using. So that is a very common mistake that people make. They hit something like right on the line and they just, record the number that's there because they know what the number is right on the line. They're not really sure how far they should go. So it's really important to do that. Again, if you're not sure, you can take that smallest marking, divide it by 2, and that will give you plus or minus 0.05 centimeters, which is 2 decimal places. And that tells you, again, how far you should take the reading to. We could actually include that once again with our measurement, plus or minus 0.05 centimeters in this particular case. Any questions on that there? So again, it's really, really important not to just kind of leave off some numbers. If you have the ability based on the equipment that you're using to go to a certain number, you do need to go to that number, even if it means that you need to put zeros to get to that sort of position. Otherwise, again, you're making your measurement a lot worse than it definitely should be. Any questions on that there? Yeah. 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 So I'll put it this way. For me personally, maybe after these first couple of experiments, we might not put it on there. I hear some people in 1A and stuff want you to kind of put that in with it, but that is how you get it. Basically, you figure out what the smallest markings represent, you divide it by 2, and that'll give you what they sometimes refer to here as the uncertainty in the measurement. And that's where the plus or minus part comes from. The added benefit of doing that is, again, if you divide it by 2, it'll tell you how far you really should take the reading. So again, in this case, when we divide it by 2, we get 0.05, which is 2 decimal places, which basically tells us that's how far our real reading should be, to 2 decimal places and stuff like that. Yeah. Other questions? In general, you could go, like I said, one more place to the right of the smallest marking. But again, not in all cases, like the example we just did there, where it was 1 milliliter to the whole number there. So again, that's how you get that smallest marking divided by 2. Other questions? Yeah. Yeah, so if you're asked to record this part, if you're asking, as long as you put it correctly, it's fine. I don't really care how you don't have to show the work for that if you want, but yeah. But in case you're not sure how far you should take the reading, but you feel pretty confident on what the smallest markings represent, that's a good way to know how far you should take the reading. Just divide those smallest markings by 2, and it'll tell you basically how far to take it. Yeah. Other questions? Yeah. All right, so that's what we did. So as we've been talking about, it is custom when we do take a measurement to again record all those certain numbers plus the first uncertain number. The first uncertain number is also sometimes referred to as the estimated digit. Some people call that. Again, when you do that, that pretty much gives you the significant figures for that particular measurement. And again, that uncertainty is really, as we'll talk about a little bit more as well as we go through it, again, not always going to be the last number written, but it should always be the last significant figure. So we'll talk about where maybe that is different as we go through it. This brings us a good point to talk about the difference between 2 words, which is accuracy and precision. Accuracy tells us how close a measurement is to the true value. So if you're really accurate, that means that, for example, in your experiment, you got very close to what the true value, the right answer should be. Now, precision refers to how close a set of numbers are to one another. So precision looks at, you did a bunch of trials, for example, and did you get kind of the same outcome every time you did it? Are each of your trials, for example, very close to each other? So the classic example, as we'll see a picture in just a second, is like the bullseye example. If you're throwing darts, for example, the goal there is to get the bullseye in the middle. So if I throw my darts, for example, and I hit here, maybe I missed the board. Oh, I got 2 of the 3 on the board. I suppose that's good. Am I very precise? No, they're kind of all over the place. Clearly, I missed the board completely, right? Am I accurate? Not really, because I'm trying to get the bullseye right in the middle of the board there. So I'm neither in this case. So I pick up my darts here and I throw them again. And I go boom, boom, boom. Am I accurate? No. Am I precise? I'm precisely not accurate, right? Which means it brings up a really good point that you could actually be very precise in the sense of you could do the wrong thing the same way every time, right? But it's still wrong, right? So you could have consistency in doing something, but you might not be very accurate in what you're doing. So you kind of repeat the same mistake every time, you get the same outcome. So you're precise, but not very accurate. So if I take my darts there and go triple or nothing in this case, and we throw our darts here and we go boom, boom, boom. Am I accurate? Yes. Am I precise? Yeah. So I'm precisely accurate here. And that's really the goal, for example, when you do experiments, right? You want to be accurate. So you want to be close to whatever you're trying to find, right? So you want to be close to the right answer, get the right sort of value. You also want to be really precise as well, which means what we look at when we do experiments is when we do multiple trials of one experiment. So we do the same experiment multiple times. The purpose of that is to see whether or not our experiment is reproducible, repeatable. And if we have good precision, that means, again, we hopefully will get the same sort of result every time we do it. So when we do experiments, we want to be both accurate and precise. And that's what we look at in the lab and stuff. We oftentimes will look at accuracy with what is sometimes referred to as percent error. And that is a relationship of how close your experimental value is to the true value. We usually want a really low percent error when we calculate it. When we talk about precision, sometimes we look at standard deviation, percent deviation. And again, that looks at, again, if you did multiple trials, were they repeatable? Did you kind of get the same answer every time you did it, or very close to the same answer? Any questions on the difference between the two there? All right. And there's our example. Obviously here on our left there, we're inaccurate and imprecise. We're kind of precise, but not accurate. And again, here with our darts there, we're accurate and precise, which again is the goal of what we want to try to achieve. All right, so take a moment here and figure out what is the proper measurement. You got some options there, so take a moment and see which option looks like a good one. Obviously, the big lines, these numbers go to the big lines, just got moved a little bit. So obviously those guys go. Okay, so let's take a look. Once again, big marking there, 2 and 3. So that is going to be 1 centimeter difference. Starting to count here at the first marking after that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings. That's the next big one. So 1 divided by 10 is going to give us our 0.1 centimeters. So this right about here at this big marking should be 2.5. That means that this guy would be 2.6. And that guy would be 2.7, 2.6, 2.7. That means we're somewhere between 2.6 and 2.7. So definitely 2.6 is going to be our certain number. Again, in this case, kind of looks very close to the 2.7 marking. So 2.69 centimeters in this case. Again, if we take our smallest marking divided by 2, that's 0.05 centimeters plus or minus. That also tells us we should go to 2 decimal places, which we did. So plus or minus 0.05 centimeters. So that is going to be, looks like D in this case. Any questions on that one there? And again, as you can see, smallest marking was the first decimal place. We could go one more place to the right there of our smallest marking typically. Okay, so looking at this one, this is basically our same ruler, which means our large markings again is going to be 1 centimeter. There are 10 smaller markings between them, which means 0.1 centimeters. So that's 9, and this first marking here would be 9.1. So it is just past 9. It is not 9.1 yet. And again, if you're not sure, we can divide that by 2 like we did previously there. And that again tells us we should be able to go to 2 decimal places, which clearly eliminates that guy, and eliminates that guy. In terms of multiple choice, our process of elimination is there. Without the multiple choice, again here, we know it is not 9.1 and it's not 9. So it's got to be somewhere between that. And again, this looks very close to the 9 marking. So they went with 0.02 plus or minus 0.05 centimeters in this case. Any questions on that measurement? All right, so take a reading on this one. What should the reading be in this graduated cylinder? Okay, so let's take a look. Once again, we're going to look at the large markings, which obviously here is 30 to 40 in the region of the graduated cylinder we're looking at. So our large marking is going to be 10 milliliters in this case. If we count up our markings after the first big marking, so that's 1 marking, 2, 3, 4, 5, 6, 7, 8, 9, and again, stopping at the next big marking, that is 10. So 10 divided by 10 tells us that each of our smaller markings, and again, this case is 1 milliliter. That means that this guy right here would be 11, 12, 13, 14, 15, 16, 17, 18, 19, not really 19. I guess that's 31. That would be much better, huh? 32, 33. Those all 30s. There we go, 39s. So 31 through 39, obviously there. So we could see that if we look here, we're at 36 mark. That is our 37 mark. So we're between 36 and 37. So we do know that our certain number there should be 36 is all of our certain numbers. Once again, it's not exactly 36, not exactly 37. So you may feel it is halfway between the two markings. So we should go one more place to the right of the smallest marking here and record milliliters. Once again, if you divide that by 2, that's going to give you your plus or minus 0.5 milliliters and 0.5 milliliters in this case. Any questions on that one there? How many significant figures would this have? It would have 3 significant figures. Uncertain digit is the 5. Yeah. Any questions on that there? As we talked about, I think last time, you always want to read from the bottom of the meniscus. In most cases, most meniscus will make that curvature, that kind of U curvature. Some will go the other way, but 99 times out of 100 probably is going to be the U sort of shape. The idea, as we talked about perhaps last time, is there's an attraction between the liquid and the glass container, so it kind of rises up the sides. The true volume is where in the middle is not in contact, so that's truly where, the volume of the liquid is. All right, let's see here. Hopefully they agree. That's good. Oh, they actually want us to see. So 36.8, they felt it was closer to the 37 line. So again, that is perfectly fine as well. And again, that's why we call that our uncertain number, right? I looked at it, looked like 5 halfway. They looked, it was a little bit more. So that's all good. All right. Now, this is a burette, which is a little bit different. This is a piece of equipment that we do use a lot in chemistry. A burette is something where we actually add the liquid there from the top and we dispense it out the bottom. So when you look at when you look at the scaling on a burette, it is different. What you will see is towards the top, for example, that is like where 0 will be. Then it'll be 1, then it'll be 2, then it'll be 3. The scaling actually increases as you go down on something like a burette, because again, you fill it from the top, it comes out the bottom. So as you drip it out the bottom, you're actually giving more volume. So for example, when you have a volume level, something like this is actually going to be 1 point something, not 2 point something. So you do want to make sure that you read it correctly and sort of know which way the scale goes. This is different than, say, a graduated cylinder that we were just looking at, because in a graduated cylinder, although you do fill it from the top, it actually comes out the top as well. So the scaling starts at 0 on the bottom and kind of goes up. Here it's the opposite, 0's on top, and it increases as you go down. So when we're reading this, we always want to make sure we do the same thing. We look at the sort of numbers between the big markings and we do take it, but you want to make sure you do a proper reading. Also, very common, people, for example, these burettes are sometimes, say, 50 milliliters, for example. And very common, people will record their values incorrectly. And what I mean by that is they'll go use this piece of equipment, they'll fill it all the way up to the 0 marking, and then they'll record 50 milliliters because the whole thing is 50. And that is incorrect. So never do that when you're using a burette. You should always record exactly what the number says on the scaling. And again, you got to remember that it does increase as you go down so that you do get the proper volume reading. So here, if we take a look at it, there it is. It's kind of blown up. So as I mentioned, as you can see, that is 28, and we're going down. It increases to 29. So our large markings here is going to be 1 milliliter. Now, if we count up our markings, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So again, our small markings in this case, 1 divided by 10, 0.1 milliliters. That also tells us that we could typically go one more place to the right of that when we take this reading. Again, if you divide this guy by 2, you get plus or minus 0.05 milliliters, which again tells you could go to 2 decimal places. So here, as we're coming down, this is 28.1, 28.2, 28.3, 28.4, 28.5, 28.6, 28.7, 28.8, 28.9, and then obviously 29. So that means that our meniscus is in this ballpark here. And again, remember that it is increasing. So depending on sort of what you're looking at, we could see what they went with here. I think they did 28.85 milliliters plus or minus 0.05 milliliters. Again, it was between that 28 and 29, 28.8 and 28.9. So halfway there gets us our 0.5. Any questions on that reading? So that again is a piece of equipment, probably one of the few pieces of equipment like that that it sort of increases as you go downward in terms of the scaling. So you want to make sure you take the right reading. And again, as we can see here, it is below the 28.8, but not at the 28.9. So somewhere in that ballpark. Any questions on that there? All right, so take a reading on this one, see what you think it should be here based on the scaling. Okay, so once again, we're going to look at the scaling. And again, the thing we want to see is as we go down, it is increasing. And also, again, this is something where it would actually be dispensed out the bottom. That's really what's referred to as the stopcock. It's kind of the open on. And when you open that again, it drips out the bottom basically. So if we take a look at our scaling here, we see 20 there increasing to 30. So once again, our large marking is going to be our 10 milliliters. If you count it up, we got 10 markings between each. So we got 1 milliliter. And again, in that case, if we're not sure, we could divide it by 2, gives us 0.5 milliliters plus or minus is really how far we should go. So looks like right on the second marking there. So that should be 22. And in this case, we are in a situation where we know based on the scaling that's on this piece of equipment, we can take it to 1 decimal place. So we should take the reading to 1 decimal place in this case. And we will end up with 0.5 milliliters. Not 0.5, sorry. It's exactly, so 22.0 milliliters since it's right on there, plus or minus 0.5 milliliters in this case. Any questions on that there? So that looks like maybe D in this case. Looks like a winner. We would not do C either because based on this scaling, we cannot do C because we don't have that much type of marking. So just like it's important not to get rid of, say, a 0 if you need it, it's also important not to put an extra 0 in there, just to hedge your bet that maybe it's better with an extra 0 if you don't have the ability to go that far in this case. Any questions on that there? Okay. All right. Questions on how to take a measurement? So obviously we've been talking about significant figures and really where they come from, which obviously is through measurements. Let's talk a little bit about the rules for counting significant figures. So the first rule for significant figures is any non-zero is considered significant. So when we start counting, we always go left to right, and we always start on the very first non-zero, which in this case is a 1, 2, 5, 9. They're all significant. So that should have 4 significant figures, this particular number. Now, zeros is the ones that sometimes give people some issues. So there's really 3 types of zeros. The first one's a leading zero, and leading zeros are not significant. So you could have as many leading zeros into that first non-zero number, and they will not be significant. So here again, going left to right, these are all not significant. We do not start counting until we hit the 4. That's our very first non-zero number. The 4 and the 9 obviously are non-zeros, which makes them significant. So this guy would have 2 significant figures, the 4 and the 9. The next type of zero is one is sometimes referred to as a captive zero, a trapped zero. These are zeros that are between two non-zero numbers, and they are considered significant. That means, again, starting left to right, we're going to start counting here at the 5 since that's our first non-zero. These guys are trapped, which makes them significant, so that's 3. And our number at the end there is non-zero, which also makes it significant. So this would have 4 significant figures in this case. Again, we want to go left to right. We do not want to start counting until we hit that very first non-zero. Here, trailing zeros at the right are only significant if they're written with a decimal point. So pretty much they're only significant if there is a decimal point in the number, basically. If there is no decimal point actually written in the number, then all the zeros that come at the end are not significant. But if there is a decimal point written anywhere in the number, it doesn't have to be next to those zeros, it will become significant. So if I had something like this, 600 written like this would have how many significant figures? It would actually have just one, which is the 6, as there's no decimal point written, so those zeros at the end are not significant. Now, if I wrote it like this, 600 with a decimal, now those zeros at the end will become significant, and all 3 of these guys would be significant in this particular case. Any questions on that there? So if we look at something like, say, 12,000, how many significant figures does it have written like that? It does only have 2. The uncertain number is which number? Got quiet. The uncertain number is which number? It is the 2, right? Remember that significant figures is all the certain numbers plus the first uncertain number. So since this only has 2 significant figures, that is your uncertain number. You're basically saying if you give this measurement, I think it's 12,000, but hey, maybe it's like 13,000, or maybe it's like 11,000. A lot of room for error there, right? That's a pretty big, maybe somewhere in that ballpark type of thing. So that's a pretty crappy measurement, right? By the way, if by some chance we could make this measurement, how many significant figures would it have? It would have 5, right? All these would be significant because there is a decimal point. The uncertain number in this case would be which one? It would be the last 0 here, yeah? Now this measurement is saying, I think it's 12,000, but could be like 12,001, could be 11,999, right? A much better measurement in a sense, right? A lot less room for error there. It's not like a big giant field of error somewhere on the baseball field, right? It's like between these 2 spots and stuff like that. So this is what I was saying earlier. Not always is the estimated digit or uncertain digit the last one that's written, but it should always be the last significant figure that is written. So whatever the last significant figure that's written in that measurement should be where the uncertain number lies. I will say probably 9 times out of 10, it's going to be in a lot of cases the last number that you write, but it won't always be the last number. So just keep that in mind, but it should, again, always be the last significant figure. I believe we talked about scientific notation here, right? Yes. And yeah. Okay. So a reminder again that with scientific notation, any number, right, that's written before the times 10 part is significant. So if we had 1.25 times 10 to the 2, this would have 3 significant figures because of the 1.25. If we wrote 1.3 times 10 to the 2, this would have 2 significant figures. If I wrote 1 times 10 to the 2, this would have 1 significant figure. So in scientific notation, whenever it's written in scientific notation, the number before the times 10 part is always significant. The nice thing about scientific notation, as I might have mentioned, is sometimes the only way to give the answer to the right number of significant figures is to write it in scientific notation, because you could kind of control how many significant figures there are. That is why when we look at a number, say like 0.003200400300 centimeters. Not sure how you did that measurement, but let's say we had that. How many significant figures would this one have? I'm not even sure. I wrote a lot of numbers there on my count. Well, let's see. We'll start here left to right, right? So starting left to right, are these significant? They're not, right? This is where we should start counting, right? So that's one. There's two. These are zeros that are trapped, which means they are significant, right? That is significant. We got a couple more zeros that are trapped, so they're significant as well. We got a three that's significant. So that leaves us these zeros at the end. Are they significant? That is yes and no. One of those should be right, I imagine, right? So way over here, right? There is a decimal point, which makes those zeros at the end significant. So again, the decimal point does not need to be near those zeros, just needs to be written somewhere in that number. I don't even know how many that is. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 sig figs in this particular case. Any questions on that there? So if I had 0.00300, right? How many significant figures does this have? It does have three significant figures, right? If I write this in scientific notation, we're going to go 1, 2, 3 places times 10 to the minus 3. Is that correct? How many significant figures does this one have? I just wrote in scientific notation. It has only one significant figure. Did I just lose significant figures when I did that? I did. We can't do that, right? So you cannot lose significant figures. So because this has three significant figures, when you turn it into scientific notation, that is why you do need to keep the zeros in this case. And that will now give me three significant figures, which matches the three significant figures I have there. So whenever you write a number in scientific notation or take a number from scientific notation to decimal form, the idea there is you shouldn't lose any significant figures along the way. So again, that's why in certain cases we may keep certain numbers and certain zeros, and in other cases, obviously we might get rid of them. If I had this number here and I want to write in scientific notation, it actually should be 4 times 10 to the 2 because this has one significant figure and now this has one significant figure. If I kept the zeros here, same idea, this would now have how many significant figures? It would have 3, right? Which again is more than I started with. So it can't gain significant figures along the way. So you do want to make sure you maintain the significant figures as you go from, like I said, scientific notation and backwards. Any questions on that there? Now, with that being said, like I said, if you had something like 12,000 that we looked at a second ago, and I wanted to write three significant figures, there is no way to do that, right? There's no way to write three significant figures in a decimal sort of form. If I wrote 120 like that, is that three significant figures? That is 120 and 12,000 the same? It is not. So you can't do any weird like rounding or stuff like that. So the only way we could do that is scientific notation 1, 2, 3, 4. 1.20 times 10 to the 4. Again, if we wanted three significant figures, that would be the only way to get that number to the proper number of significant figures, still maintain what the value is. Any questions on that? Yeah. We would do the same thing. We would go 1, 2, 3, and then we would go 3.2004003,000 times 10 to the minus 3. In this case, we would need to keep all of those numbers, technically speaking, because all 11 of them are significant. Yeah. Other questions? Okay. So again, we want to be careful on that as well, as if you happen to give an answer in scientific notation, don't lose significant figures, along the way as well. Other questions on that? All right. Now the third type of number here, after I wrote all over the page, let me clear it here. There you go. And number, which is not necessarily a significant figure, besides significant figures, which are usually from measurements and stuff like that, where we have some degree of uncertainty. There's actually numbers which are considered exact numbers. And exact numbers are really obtained one of two ways. They are, for example, obtained by counting or some type of definition. So, for example, if I had a bunch of pens up here on my desk, I'm not going to do any type of experiment to figure out how many pins I have. I'm just going to simply count how many pins I have. The classic textbook example is like if you have a basket of apples, you're just going to count how many apples are in there. You're not going to do like an experiment or something like that, or a measurement really to do that. More commonly, the way we find them is in definitions. For example, 1 inch is exactly 2.54 centimeters. 1 pound is 453.6 grams. Truthfully, it's a few more digits, but we'll go with that. They want you to learn that in this class is exactly. 1 foot is 12 inches, 3 feet in a yard. 1 mile is 1.609 kilometers. Also, there's a few real more digits, but we'll go with that for this class. And again, if you have something like 9 pencils, that obviously is something that you would just count and stuff like that. So what's the deal with exact numbers? Exact numbers, and by the way, each of these things are what are referred to as equalities. These are equalities. Equalities are basically two values which are on different unit scales, but represents the same amount of something. So for example, if you had $1, that is the same amount of money if you had 100 pennies, right? So they both represent the same amount of money, but they're on different units. So is they could have an unlimited number of significant figures, which means really if you come across something that's an exact number, you have as many significant figures as you really want. Where this really comes into play, as we will talk about, and by the way, I think I mentioned earlier, and I might have wrote most of these on the previous slide, but they do want you to kind of know these, yeah? So make sure that you do know these. Where this comes into play is if you are doing some type of calculation that has an exact number in it, we pretty much do not have to worry about that exact number in our calculation in terms of how many significant figures our answer should be. So we're going to talk about, how far we should take our answer, how many significant figures our answer should be in calculations. But pretty much if you have anything that's considered an exact number, you do not have to worry about it in your calculation. So we talked about two types of unit scales, which is English and metric. So if you're using any type of English to English sort of conversion, that's considered an exact number. If you're doing metric to metric, that's pretty much considered an exact number. The only place where you really have to worry about it in a calculation, as we'll talk about, is if you're going kind of English to metric. In most cases, outside of some of these here, they're not considered an exact number. Obviously, we have some English to metric ones here, like an inch to 2.54 centimeters, a pound to grams. Those are considered exact, but outside of those, you do have to sort of take them into account. They're not considered exact numbers, but these are considered exact numbers. If you're doing any type of, again, metric to metric sort of conversion or English to English sort of conversion in terms of units. Any questions on that there? All right, so take a moment here for each of these. How many significant figures we got? All right, so let's take a look. Once again here, starting with first, we're going to go this way. We're not going to start counting there to the 3. The 0 and the 4 are significant, so we got 3 significant figures in this case. This is a number written in scientific notation, so that is going to be 4 significant figures in this case, yeah. By the way, when we do look at a number in scientific notation, as we just talked about, all those numbers before the times 10 part are significant, but sometimes when people, for example, have something like this, for example, they oftentimes will sometimes just turn it into, go 1, 2, and then 3 into a number like this, and they'll write like it has 2 significant figures. So you don't want to do that. If you, again, it is written in scientific notation, do the how many significant figures from the number written in scientific notation, not after you kind of convert it into like a regular number, decimal type number. So again, if it was written in that scientific notation, it's important, those numbers, and that's why it would have 3. Here, all these would be significant, so that's 3. Here we have no decimal, which means this 0 is not going to be significant. So really only the 1 is. And lastly here, starting to count here, significant, significant. Once again, the 0 is going to be significant because of the decimal point over there on the left. That looks like 4 in this case. Any questions on any of those there? All right. So obviously here, if it's a patient who weighs 155, that's something that's going to be measured. Basket holds 8 apples. That would be an exact number. That's going to be something that you counted. 1 kilogram is equal to 1,000 grams. That's a metric to metric conversion. So that would be considered an exact number. And the distance from Colorado to Texas is 1,720. That obviously is going to be something that's going to be measured along the way. So let's talk a little bit about rounding and calculations. When we do any type of calculation, we do want to round to the proper number of significant figures when it's all said and done. We don't want to do any crazy round. So normal rounding rules apply. If it's less than 5, you just kind of drop the digits. And if it's more than 5, the next number that you're going to want to round upwards by 1. We once again, if we look at a number like 13,333, and if I want 2 significant figures, what should that be? Should it be 13? Should it be 13,000? This has how many significant figures? 2. This one has 2. They both have 2, actually. Yeah. Is there a difference in those numbers? There is, right? If I owed you, for example, $13,333, and I said, no problem, here's 2 significant figures, here's my $13. Probably not going to be very happy with me, right? So there is a very big difference in the meaning of like $13,333 versus say $13. So we never want to do extreme rounding, and it happens a lot, especially when people try to get the right number of significant figures in their answers. So they kind of just go crazy with the rounding, like, all right, I know if I just cut everything out, that's like 2. So I'm going to stop right there. So we never want to change the meaning of a number. This again would be the right way to do it, as we have 13,000 written like that with no decimal point, has 2 significant figures. So 13,000, 13,333, pretty much the same number. Maybe I get like a $333 teacher discount, not bad. But basically means the same number, right? So don't do any crazy rounding for sure. You don't want to do that. So for each of these, round these off to 0. The rest are non-zero. So we do want to go to our second significant figure, which is there. We do want to look at the number next to it, which is a 7, which means we do want to round up. So 36 meters in this case for 2 significant figures. Here, this would be our second significant figure. Once again, we look here, and that is less than 5. So we're going to drop those numbers. So 38, we do need the zeros here to maintain the value. Should I put a decimal at the end? I should not, because then it would have 4 significant figures, right? So we don't want to do that, but we still need the 2 zeros to maintain the value. Second significant figure right there, so 0.0026. That being a 2 means we could just drop the rest of the numbers there. And lastly here, that's our second significant figure, so 1.3 kilograms in that case there. Any questions on any of those? All right, so let's talk about really for calculations, how we determine significant figures. And there's kind of 2 grouping of math sort of calculations that we do. One is multiplying and dividing. When we multiply and divide, we actually look at significant figures. And it is the number with the least number of sig figs is what your answer should have. So whatever number in your calculation, if you're multiplying or dividing, has the least number of significant figures, that is how many significant figures your answer should have. So for example, if we took 4.25, we times it by 1.2, and we do that on our calculator, 4.25 times 1.2, we end up with, on our calculator here, 5.1. In terms of significant figures, that is 3 significant figures. That is 2 significant figures, which we got lucky in this case. Actually, we should end up with 2 significant figures in this particular case. Again, the one with the least number of significant figures is pretty much your worst measurement. And you're only as good as your worst measurement. So that is why we look at the least significant figures for our answer, because your calculation is only as good as kind of the worst one. Now, the other thing that we do is add and subtract. And when we add and subtract, we actually look at decimal places. And the answer should have the same number of decimal places as the number with the least number of decimal places. So if we had 4.256, 1.1, 3.0010, and we're going to add these, we'll end up with 0, 7, 5, 3, 8. When we go for our answer in this case, that has 3 decimal places, 1 decimal place, 4 decimal places. That means we should end up actually at 1 decimal place, again, the same as the one with the least number of decimal places. We do need to actually round up in this case, since that's a 5. So we actually should end up with 8.4. 8.4 in this case has 1 decimal place. How many significant figures does it have? 8.4 has 2 significant figures. So those are 2 different questions. And that's really important because sometimes we do combination calculations, right? Sometimes we're multiplying and adding and subtracting everything together. So you do want to kind of keep track of your significant figures. I personally would not round till the very end of your calculation, but you should keep track of what's going on. You should keep an extra couple of digits. Don't round too much. Those are sometimes referred to as guard digits, so you can keep some extra digits along the way in your calculations, so you don't get any. Example, if I did 3.25 times 1.111 divided by 3256667. Here, the first thing that we would actually do is multiplying, which means we should be looking at significant figures. Our top number here has 3. This guy here has 4, which means when it's all said and done, we should really end up with 3 significant figures doing that top part. We then would take 3 significant figures and divide it by our bottom part, which has 2, 4, 6, 8 significant figures. That means that technically speaking, our answer should end up with 3 significant figures along the way. So if we did that, 3.25 times 1.111 divided by 3.256667. We end up on our calculator with something like 1.1087255577. In this case, we should go to 3, which is here, which means we should end up with 1.11 as our answer, which has 3 significant figures. Questions on that? So definitely you'll be doing combinations of these things. You should keep track, keep a few extra digits. Personally, for me, when I'm doing calculations like this, multiple source steps, I just roll with the whole number in my calculator until the end and kind of clean it up at the end. If you want to write a number down, take it to a few extra digits of where you should end, and you should be okay. The problem with rounding strictly after each step of your calculation is you'll kind of move yourself further and further away from the right answer with the rounding error. So you don't really want to round too much until the very end, definitely. Now, for example, if we had, let's go with 3.1 times 4.77 divided by 32.5. And then let's add it to 0.1135. Go for it. What should you get? I'll do it as well since I just made it up. So we obviously would do the top part there first, to 3.1 times 4.77. On your calculator, you got something like 14.787. Really here, we're multiplying, so we're looking at significant figures. So that is 2. That is 3, which means really this answer should end up right about there at the 4, right? I'm not going to round at this point, but I'm just going to kind of keep track of where we should kind of be ending. We're then going to take that top number, which technically should be 2 significant figures, divided by the bottom, which has 3 significant figures. So now really our end result here should have two significant figures, right? The least of what we're doing. And if you do that, and again, I used the whole number there, 0.454984615. We now know that we should end up with two significant figures, which does take us to this number right here, which is 0.45, really. We're now going to add, which means we should technically be taking 0.45 plus this number here, which means we now should go to decimal places. So if we add that there plus 0.1135 gets us 0.568488615. Once again, I'm not rounding my number at this point. I'm just taking the whole sort of value with me. And here we will end up with two decimal places, four decimal places. So really right about there. So 0.57, give or take. Now, clearly, if you rounded at the 0.45 aspect of it and added it to 0.1135, you'll end up with 0.56, which is pretty close anyways. But again, if you didn't round to the very end, you'll end up with 0.57, which actually is where we should end, because again, the last thing that we did was adding in this case. So we want to look at decimal places. So you kind of want to keep track of everything. And sort of your last calculation, whatever you may be doing, sort of will determine kind of where you end up in terms of your final answer. Any questions on that there? Now, one thing that you don't even need to take into account is any type of exact number. So if you're doing any type of, again, multiplying or dividing, adding or subtracting that involves sort of exact numbers, you don't have to worry about them in your calculation. Most of the time is multiplying and dividing where that will come into play. You won't have to really worry about it in terms of your answer for multiplying and dividing. Any questions on calculation of significant figures? All right, we were rapid there for today.